Hello, hello. So we have finally now the last talk of the conference. The topic is a really interesting one as well. I mean, as you might have heard about design patterns, usually they are like, these language agnostic things, solutions that people recommend to do in different situations. Maybe if you're doing graphical applications or website, the MVC pattern, or maybe, I don't know, if you are doing other things, you have like adapter, factory, singleton patterns. But now, we have now Azure that will talk about a really interesting one, which is the composite pattern. I would like to invite now Asher to the stage. Hey, Asher, how are you?
Fine. How are you? Good to see you.
Good, good. What time is it? Where are you joining
It's
from?
9:30 in Tel Aviv. Nothing.
Ah,
Not 9:30 in the morning. So it's
perfect, perfect. So only 1 hour
perfect
ahead of.
time for presenting, right?
Exactly. Cool. So I can see your screen here. Now it's on the stream, and I will not take more of your time. And good luck with the presentation.
Thank you. So let's start. Hi everybody. I'm going to talk about particular implementation of composite design pattern in Python, providing some rationale why did we do it and how we did it. Couple of words about myself. Normally some with joke that people do not live so long in our industry. Well, I'm an exception maybe, but I really like what I'm doing. My areas of interest are cloud architecture, domain-driven design, promise theory, and complex adaptive systems. Here are some links when you could find more information about my. I will post this presentation on SlideShare right after the conference. So topics to cover today. I really want to spend most of the time on implementation. So I will pass through preliminary stuff quite quickly. But if you have questions, just stop me and ask them. So brief introduction into design patterns topic. More definitions, formal definition is existing on Wikipedia. The story started in the previous century by a seminal book called The Timeless Way of Building. If you like some kind of techno-philosophy poetry, it's a good reading, really, and the original idea of design patterns came from here. It was generalized by community, and in mid-30s, mid-90s, was a seminal book of design patterns published by these four guys. It's a book called Gang of Four. It's still fundamental in this area, but examples are a bit outdated. They are mostly in C++ and Java. There's a good GitHub repository and examples of implementing design patterns in Python. So we recommend it. Let's move. So composite design pattern. When we need it, it's a good candidate whenever we have any form of nested recursive or tree-like structure, be it file system or code structure or any hierarchical data structure is a good candidate for that. The official implementation looks like as follows. We have a normally abstract base class or interface with one or more operations, normally abstract. We have one or more implementations of that abstract interface. And then if we want to treat a collection of these different implementations as yet another one, actually implementing the hierarchical structure, then we derive a composite from this base interface and define the same operation, which is some form of iteration of a child. And here the object structure of that implementation. It has some limitations. I need to overload overload depends on which language you're coming from. All methods in abstract interface. While implementation is mostly trivial, I need to go through childs and perform some, invoke corresponding methods and perform some aggregation. I could go depth first or breadth first, but very often people don't care which one. And that's okay if the number of methods or base class interface is stable. That was not my case. So I will give you a background where I started from. This activity, relatively new one, kind of considered continuation of infrastructure as code. Here's infrastructure from code. And the challenge is to pick up plain Python application code with some configuration also in Python, and to translate it into 4 different interactions with cloud services, like acquire resources, configure resources, consume resources, and operate them in terms of monitoring, alerting metrics on different clouds. And the point is that we have different services, some of them coming from different vendors, they have different levels of APIs, and could be located, deployed in different locations. So it's a pretty challenging structure. I recently published an article on Medium describing this mechanics. So at the heart of that translation activity, we treat cloud as a hardware, and we just built an operating system for it with compiler. So I had a resource template builder. One of the APIs to communicate with cloud services is so-called orchestration engine, for example, CloudFormation on Amazon or Terraform on Terraform. And I need to build 2 groups of elements, descriptors for here, right? One is the general service level, and another at the individual function level. Again, details are less important here, but I came up with the need to keep them as a composite. Why? Because every high-level feature, like I want MySQL database, but MySQL database is translated into multiple resource descriptors on CloudFormation, for example. And it might have different variants inside, sub-features. For example, do I have encryption? Or do I need to put my database in a virtual private cloud, which is called private network? In other cases, what form of user authentication I need, or which interface I want to interact with this service. I could interact with MySQL through DB connection, plain DB2 API, or SQL Alchemy, for example. And that led me to some kind of deep nested hierarchical structure that I need to build dynamically from configuration. And here we come to a very important topic, maybe one of the most important in this conversation. Is called design pattern density. Design patterns seldom come in isolation. You seldom use only one design pattern. You put multiple design patterns together, and that is considered a certain metrics of design maturity. However, novices very often mess up themselves. If it's not done correctly, it's a disastrous over engineering. In my case, I hope it was not. So we have a bunch of design patterns applied simultaneously. Right? First of all, this is a builder design pattern, right? Which builds out resulting template, be it CloudFormation on Amazon or Terraform or ARM on Azure or Deployment Manager on Google. But I also applied null object pattern, which actually says provide default implementation of these methods, returning nothing. Because every individual resource per template builder will need to implement only some subset of these methods, and you don't want to repeat them. Then we have composite design pattern and iterator together. I will justify it shortly, which puts them together in nested hierarchical structure, implemented in a form of class decorator. So it's a decorator design pattern. Building of this hierarchy of creation of this hierarchy of builders is done through factory method. which looks at specification. In addition, I created another decorator, which goes the decorator. Not essential for that discussion, but it's just funny observation. Now let's look at the code. Composite design pattern, we just use Python decorators. At this wonderful conference, we had very interesting presentation about Python decorators. So basically say composite, make this class composite from that base class. That's it. So as a side observation, it actually behaves as a pass-through gate, because if I don't override these methods, it will call them. As a complementary part, as a decorator that blocks them unless I do otherwise. Interesting observation. It allows creating a quite sophisticated logic of access control management and all this stuff. Now we go to how we implement it. It's an interesting Python meta programming exercise was for me. And I hope you will get some ideas, understanding that you could do a lot with Python meta programming if you need to. Python decorator is just a function that as a parameter gets a type class and returns type. So we just get input type and return other type. Now, what I need to do here, I could create type dynamically, this line, providing its name, base classes, which I steal from the original class, and a dictionary of attributes. Now, I build dictionary of attributes by calling an internal function make method. We will see it in the next slide. By traversing class members, which are functions. This comes from inspection library of Python. And I skip over private method. That's questionable decision, because by that I also filter out magic methods, but that's current implementation. In addition, I specify a constructor for that new class, and I make it an iterator. The whole code structure is a kind of top-down decomposition. I specify what I need at high level, and then I just go into details. Constructor is quite trivial. I just need to store all parts or childs as my internal attribute. That's not complicated, right? In make method is where real stuff is done. Let's recall the original idea. I need to take original method specification and convert it into iteration over child class objects, calling this method one by one. There's a difference. The difference is whether I'm dealing with void method, which returns nothing, or it returns something. How could I detect it? I could use introspect signature library, signature function, get the function signature, and look at return annotation. Now, Python with type annotations creates a certain challenge. It could be normal type, like integer or tuple, without any bracket parameterization, or could be something like that. For that reason, I need to strip down annotation parameters, and I could ask for origin if it's not none. If it's none, I take just original type. And then I could analyze. If it's none, I need to create some form of for each iteration. And if it's not none, if it returns something, I actually, as we said, as we discussed, it's an aggregation of child objects invocation. So it's a reduced algorithm, right? So again, it's top-down decomposition in action. Pay attention that I just specify to high level what I want to do, and then I go one level deeper and deeper and deeper. make which is pretty boring. I just run for loop, extract. Let's not forget. I get a method name here, right? It's a method name, and I define inner function. In decorator presentation, it was discussed in more detail. There is a so-called Python closure gotcha. Very roughly speaking, parameters are passed by value in Python, but closures are captured by pointer. If I don't specify inner function for that, it will always point to the last method. So I define inner function that will retrieve from every object, and self is iterable. We'll see it shortly. Retrieve the method by name from that object and invoke it, passing args and keyword args. So this way I created a new function, new member function, right? Because it gets self for any original function of the base class that will go through parts, through child objects, and invoke them one by one without treating any return value because there is no one. And it just creates a function on the fly, right? In Python, metaprogramming functions are first-class citizens. Make reduce is more interesting because here, the same problem of closure gotcha, I need to define internal function. But in addition, I need to do more things here, right? First, I need to get initial value for particular return type. Apparently, it's just calling this return type with parentheses. And second, I need to detect which combination method to use. And here is probably the most interesting part of the solution. If it's integer, string, or tuple, I could use add operator. I just could use plus. But if it's something else like sets, lists, or dictionaries, there's a remarkable library called deep merge that performs deep merge of this data structure. So I could take one dictionary, another dictionary, and merge them together, not overwriting. This is pretty cool stuff. Okay. And then we just invoke reduce algorithm, all right? Providing init value and combination, combining the outcome of calling that function. Iterator is interesting. It's most tricky. It's built on top of DQ, but I didn't write it. I just stolen it from Stack Overflow. It's a cool algorithm of deep first traverse, but I will not get into details here. If you want, could take it offline. And now we will look at another more, in a sense, advanced use case. I also need, because our compiler system compiles to Cloud Functions and Kubernetes from the same source, we need to build Kubernetes manifests. And guess what? Kubernetes manifests is also composite of different parts, each one with its own details. But the point here is that I need all of them. I don't have specification. At the moment, I just needed to collect all of them. And here's a nice trick we could apply. Again, playing with basic Python facilities. I could just traverse models on the same path I have, import them one by one. And since they all these subpath builders are in the same package, they will be collected by Python and subclasses magic method. And then I could create a composite for that. It was pretty cool because the original version of guys who developed it without using composite, they get a very long monolith function of generating Kubernetes manifests with a lot of conditional logic inside and a lot of duplication, and that just shrinks it down by an order of magnitude. Now, let's look at concluding remarks here. Um, I did not implement visit or pattern. It could be done. It's not complex. I did not have any strong reason for doing that. But if somebody does, drop me a line. We will consider it. The current set of aggregation functions is still a bit limited. We had a presentation at that conference about functional programming in Python. So in functional programming, they very often use, especially in Haskell, use the concept of monoid. Monoid is a special set of data type and operation when you have initial value in some accumulation. So with the current implementation, I only use add or deep merge, but I cannot multiply. So that the current implementation, for example, automatically will implement any function for Boolean return values because we just add them, but cannot implement all. So we do not implement monoids here. We do not parameterize. It would complicate the interface. So I didn't want exactly to do that. But I could easily imagine that some use cases might justify using additional parameterization of what kind of monoid you want for aggregating results. The current version, and it's a good side effect of presenting in conference because it forces you to clean up your code. The current official version deployed on PyPy is slightly different, and this one is on a separate branch. We will release it quite soon. A couple of things to remember, to recall from that, to take from that. To take from that presentation, design patterns are extremely powerful, really. I mean, if you take some time to study them, they could create a difference between make and break on with solving complex problems. Usually they come in concert with design pattern density. Seldom, it's like using one word instead of creating sentences and telling the story. You need more than one in one place. Composite, very powerful when you have on-off feature logic, kind of hierarchical structure of features. And variable lists of components, you just don't want to bother to put them manually. Python metaprogramming is miracle. I mean, you could do much more probably than people think. Again, if you took the right angle to look at them, but with more power comes more responsibility, and if people start just chasing after advanced technologies, it's a sure to hell. You need to understand what you are doing. But if you do understand, it's extremely powerful. It really makes the difference. That's it for now. Any questions, I will be really happy to take. Otherwise, I will upload this slide deck to SlideShare shortly, and you can reach me out. Thank you.
Thank you very much, Asher. Yeah, I mean, that will be really great. There were many references and resources during your presentation, so it would be really cool if you could share it around and maybe on Discord server, for example.
I will upload it immediately.
Perfect.
And thanks for giving me opportunity. It's a cool conference. You don't need to travel, don't need to suffer from jet lag.
And you can be in your pajamas as well.
And you could be in your pajamas. Exactly.
Thank you very much then.
Thank you. I will stop sharing.
Okay. Bye-bye. Thank you.